We are back. Welcome to our first lecture of our online lecture series Radar in Action in 2022. My name is Jens Fiege and I'm glad that you are with us again. Here in Wachtberg the weather is still dull and grey, and it has been all winter because unfortunately there has been no snow here in the Rhineland in Germany. And because it doesn't look like there will be any more, we are longing for spring. Speaking of longing, you surely already missed the Radar in Action lectures and longed for it to start again. And now the time has come. We start with a challenging lecture by Dr. Reinhold Herschel on radar imaging and introduction to the theory behind. Please, Reinhold, go ahead.
Thanks, Jens, for your introduction, and thanks to everyone who is joining us today as Jens already said, something maybe a bit more challenging if you don't like theory, but as I see many people like theory, and I'm glad that we can do it here together. Normally at Fraunhofer we talk about applications. We talk about getting sensors in cars, we talk about factories, we talk about all the industrial applications you could make out of our sensors. But of course we are also in science. So that means there is a theory behind, and our aim is to connect that theory to your application and to make it happen. And of course, it's easier to work with this theory if you have some basics behind it and know, okay, that's what we are working with, especially if you want to start yourself with this. And so the aim of today's lecture is to enable some of you as a first step to say, okay, if I want to start with radar imaging, what does it mean and what is the theory behind? And yeah, it's nothing special, so let's follow in the content of this lecture. But of course, as I said, at Fraunhofer we are starting with applications and nice images. Talking about imaging, what's the difference of a radar image compared to other images? If you look at the left, you see a guitar. It could be a photograph, just black and white, but it's not just a photograph. You cannot only see the guitar, you can see in the guitar, you can see the inner constructions, and you can see through things. And that of course opens applications like security scans, as you might know from the airport, such as material scans, looking for enclosures in materials, for example, all the materials we're gonna need to build our windmills out of. Or you try to visualize 3D structures like this small snowman here you see there on the upper right, where you can just scan, get the feature without actually using a camera and get it completely in 3D. But of course, before you get it, you have to implement it. And the question is, how does it work? Basically, the physics behind it is like for a camera. So that's why I want to start with a camera. Some people who might have seen earlier talks know that I like to do that example because we are familiar with. I'm standing in front of a camera, and why does it focus me here at a meter distance? It focuses me because the lens is in the path of the light. So here the light is emitted and it travels quicker through air than through the lens material, which is glass, for example. So the longer way here is not passing through the lens, but the shorter way is passing slower through the thickest part of the lens. So at the end, if you're not interested what is longer, but what is shorter, basically this path here takes the same time as this path because it sees less material. And that's why they are all adding up constructively at the focal point, because it takes the same time for all of the rays to travel to this point. And that's why you get the maximum field there and this focus. So the delay or the phase shift of each signal over the aperture of this lens is giving our focus. And that is exactly what we are doing in radars. We are emitting a signal at different point of the aperture. Instead of passing it through a lens, which would be possible but a bit inflexible, we could delay it. You can do it digitally, but you could also do it analog. So you have a phase shifter here, you transmit the signal, and if a phase shift is adapted to exactly follow the parabola of this lens, you would focus exactly at the same point. the larger the lens is, the better the focus gets. So if you want to focus in a large distance, you know with telescope lenses you get pretty huge. Or the opposite is the case. If you go close to the lens, you also get a very small focus. You know it from a microscope. The closer you get, the better your resolution just before you break the glass which is covering the probe. So two factors are scaling that. One is the wavelength. The shorter your wavelength or the higher your frequency, the smaller your resolution. So with 4 mm waves, you can focus higher as with 4 cm waves. So that's why 80 GHz, for example, is a very interesting application. Gets very interesting applications in imaging. And the other factor is the distance versus the size of the aperture. So the further I go away, this larger the lens has to be. And this is basically giving us our resolution. So at 80 GHz, you could theoretically, if you have an infinitely large aperture, go to almost a millimeter resolution. While in 240 GHz, you can go a factor of 3 down in resolution and get far better resolved images. That's exactly where our technology comes into play. You can do that in hardware, but you can, of course, just send the signals here at each transmitter, receive it at the same point, save it, and then just apply a phase shift at every point. And this is exactly what the mathematics is behind it. So, as I said, you transmit a signal. This signal is traveling to an object and traveling back, so you get a time delay. The next antenna is transmitting the signal, it's reflected back, you get another time delay, and so on. So you go over the entire aperture, step by step, and get their different traveling times. When do you achieve the focus at this point? As you've seen before, you exactly achieve the focus at this point if all the time delays are basically equal. The time delay you achieve here, plus the time delay you achieve in the phase shifter. Then you get a focus at this point, and you can adapt it to each point. So the measurement signal I see here, this one marked in blue, is basically the object. So the real scene, the object, this point scatter, times the phase shift, which is depending on the time delay. Times the frequency, because the time delay is nothing else than a linear phase shift over frequency. This phase shift is given by the distance and by the speed of light, but you have to use a factor of 2 because you're going there and back. If we assume that model, we can now reconstruct the image, not only by a single signal. We now know how we focused a single signal, but we just take many signals. We know that the phase shift is depending on the time delay and the frequency. So you have to do that for all frequencies in range and sum them all up. That's done here in the first sum. So you have a certain set of frequencies, and step by step you go over these frequencies and add them all together, applying the right phase shift. The same you do for all the antennas. The physical signal you see is basically dependent on the frequency and the time delay. And if we compensate the external phase shift, this phase shifter here, to compensate exactly for these two factors, then you can cancel that cancels. And if you then add up over these terms, the phase shift cancels with the phase shift from a group delay. And if you add them all up, you end up in an image. This image is not the object, it's not the same as the object because it's just an image of the object that's had here. But technically it's representing the object. And if I can do that for a single point, I can do that for a set of points. So step by step, I focus to each point in space. I could theoretically focus an arbitrary number of points, and just knowing that the resolution is depending on the distance and the array size again. But theoretically, you could focus to each point in the scene. You can also follow a surface. Generally, you would just define a grid. As here, I show with an arbitrary object. You define, for example, a rectangular grid, define a set of points, and reconstruct focus at each point one after the other. this is not necessarily a measurement process. This is just post-processing. You're measuring once with all antennas, and then you can apply the phase shifts to all elements and focus at a set of points here in space. And if you focus on enough points in space around the object, you will see the object appearing, because it's just focusing the signal that comes from the object. If there is no signal coming from that point, nothing is focused. And this is where you get the representation of the image. You don't need any assumption for that. So you can distribute the points anywhere. You can use any frequency setting. You could use equidistant steps or whatever you like. You can do that. You're flexible, but it's numerically very complex. You have 2 sums for each point, which is massive. We call that the so-called matched filter method. That is the simplest one, but this also already gives you an image. It's nothing more than this. As I mentioned, of course, you don't reconstruct the object. Yeah? The object is just there in front of the radar. What we reconstruct is actually the image. So we get the signal reflected from the object. Here, for example, a single scatterer in space. And this ideal scatterer is scattering to our antennas. So we take a set of antennas. We could, for example, take a rectangular grid, one after the other, over the XY plane, just over an entire aperture. We are sampling the signal and measuring from each point. And then we are adding up over all antennas. Of course, it's focusing just to the maximum where the object is. So the image has the highest amplitude where the object was. Otherwise, we wouldn't get the representation. But due to the limitations of the sampling, we are not sampling everywhere. It's not an infinite plane. And we are sampling at a certain grid. You will get a certain signal also in other parts of the image. The point which we are focusing on, so the point scatterer, is spread over the image. And this is the so-called point spread function. The point spread function is a characteristic of our radar, which is depending on the bandwidth, which is depending on the sampling positions, on our antenna features. And this is characterizing how well we can resolve. So the narrower the point spread function is, the less the point is spread, the better our resolution. And it's defining our dynamic range, because as you see, you get side lobes, it's smeared. And if there are many points in the image and they're all smeared, you might lose details in neighboring points. As I said, that point spread function purely depends on the features of a radar. So bandwidth on one hand, but antenna distribution on the other. So if you're sampling over the space in a circular shape, as we see here, for example, you will get a point spread function which also sees this circular shape. Optimizing this antenna distribution, so of course you want to use as less measurements as possible to minimize the effort, and on the other hand you want to get a perfect image. Optimizing that, this compromise is an art on itself. That's part of our design work when we are building images. But at the moment, it's flexible but highly ineffective. We are adding up for all frequencies separately over all antennas. If you want to simplify that, you have to assume things. The first assumption you could easily do is I'm sampling my signal, my physical signal I see in the antenna in an equidistant way. So we are measuring frequency over frequency, and we don't measure an arbitrary collection of frequencies, but we are measuring at a certain start frequency, a minimum frequency in a certain grid. So this grid has the grid size delta f, a grid spacing delta f, and a certain number of frequency points. It's the same sum, you just take the grid expression in, and if you write this sum, you see that this term here, this sum, is nothing else than a so-called inverse Fourier transform. So a Fourier transform is a numerical operation where you transform a signal from the time domain, so something which changes over time, into its spectrum. And this is a highly effective operation since that's exactly the same mathematical expression. We can replace the entire sum just by the Fourier transform and do it far more efficient. One has to be a bit careful. A Fourier transform is a periodic operation, So depending on your frequency spacing, you might see your objects in a higher distance again. So basically, after applying the Fourier transform, you will see a certain delay in a certain bin, but and depending on the time delay or depending on the distance, you will see objects or reflections in different bins, but they might reappear depending on your spacing, because you're not spacing, you don't have an infinitely dense spacing. But of course, if you use this, you reduce the entire sum by one dimension, which is of course far more efficient. Mathematically, it's exactly the same, just as we've done before, only for equidistant spacing. How does it work in practice? Our object image is the sum over all antennas. So what needs to be compensated? The distance needs to be compensated. As I said, we apply the inverse Fourier transform and we transform the signal to the so-called impulse response. So basically I get the signal as a function of delay. As the signal part which is delayed longer appears at a different point in time as the signal part which is delayed less. So it's kind of taking your stopwatch, starting and looking what comes first, basically. That's the basic fundamental operation of a radar. You get a profile of different signals at different time delays, and now you want to reconstruct at a certain point. You know your time delay because you know the distance from the antenna to the point. You can calculate that. We did that before when we compensated. And since you get the signal resolved by time delay, you can look for the right bin and basically just after the IFFT get the right signal which has the right group delay automatically after this operation. You don't manually calculate that, you just take the right bin out. If the bins are not perfectly fitting your distance, that's not necessarily a problem. You can interpolate that, for example, linearly, that's a typical operation, and get the right signal out. So you calculate the delay from each antenna to the reconstruction point. You interpolate the right bin, take the complex signal from this bin out of an impulse response, and this is something you have to do, compensate for a lowest frequency. That is actually the phase term we see here. After the inverse Fourier transform, the impulse response as a function of delay would compensate for our phase slope. But it does not compensate for a minimum frequency because we are not starting from zero. We are starting from some 76 gigahertz, 7 gigahertz forever. And the algorithm needs to know that. So we have to compensate for a minimum frequency. And after this, we already compensated the phase, and we just add up to the signal. So we go from antenna to antenna, compensate this phase, and add up. And so our object image adds up as before. The good thing is here, it's a Fourier transform, it's a multiplication, and it's a huge sum, nothing more. That means that you can split this sum in arbitrary groups. So you can basically take 100 antennas, make this sum, and the other 100 antennas you build up a different sum. And when you add these sums together, you are really flexible. That can help in system design from time to time, especially if you think of parallelization, because all the sums are independent of each other. I said that we can see the delay after applying a Fourier transform. You can do the same thing with the direction of arrival. Here you see a group of antennas and a wave coming towards this group of antennas. If it's a plane wave, the wave will be earliest at this antenna, then at this antenna and this antenna. You have a time delay among these antennas. If you know the distance of the antennas and you know the frequency, you can work out what the phase shift is depending on the direction. If the wave comes directly in front of your array, so towards the array, it would arrive at all antennas at the same time. If it comes from some direction, you would have a slope, a positive slope from this side, for example, a negative slope from the other one. And then you can do the same thing as we've done before. A temporal frequency, frequency as we normally know it, is the linear phase shift over time. The spatial frequency is a linear phase slope over space. It's mathematically exactly the same thing, so you can deal the same way. Just apply a Fourier transform and you get your spatial frequency spectrum instead of your temporal frequency spectrum omega. What do we do with the spatial frequency spectrum? The spatial frequency, as I said, is a phase slope over time. So I can see the direction. I can see the phase slope over x and the phase slope over z in my coordinates. Depends on the direction of the wave. If I can work out the spectral distribution, I can say, okay, if I know my frequency or my wavelength, I can work out the sign of the angle of arrival where it comes from. And if I know the sign of the angle of arrival and I know the distance, I know exactly the position in polar coordinates. So in the far field, so for plane waves, is nothing else than another Fourier transform, you are done. In the near field, that's a bit more complicated, but it's just another step to be done. What we need for the object image is in order to use a Fourier transform to get the image, is the image representation in the spatial frequency domain. Because from a spatial frequency domain to the spatial domain, where our image would be, we can use a 3D Fourier transform, inverse Fourier transform. We automatically can define our image in the spatial frequency transform very easily. If we are measuring in x and y, so we are sampling the antennas in x and in y, and when we do a 2D Fourier transform, so we have in kx and ky. The problem is that now we have k left. K, as I said, is the change of a phase, the total phase of change over space. That is depending on the wavelength. That's the inverse of a wavelength, so to say. The wave vector, so this change of phase, is direction dependent. So you have an x component, you have a y component, you have a z component. And the kx squared, ky squared plus kz squared, so in all three dimensions, has to add up to the total phase change, because it has to change in some direction. We can use that. We can basically calculate the third dimension, kz, which is missing still, from a frequency spectrum. So we know what frequencies we transmitted, or what wavelengths. We know kx, we know ky, because we know our spacing, what we used. And we can then calculate kz just by this formula here. It's just the square root of the squares of the other quantities. When we know, okay, what is the minimum kz and what's the maximum kz, we see that from a minimum and the maximum value of that vector. But now, in order to apply an inverse Fourier transform, we need it equidistantly spaced. As I said before, if you want to use a Fourier transform, it's very hard to deal with not equally spaced quantities. So we need to interpolate kz on the equidistant grid. And if we do that, this is just a linear interpolation. We just take start value, stop value, decide for a certain number of intermediate steps, and that's it. That's our vector. We interpolate, we calculated kz on that, and then we have kz, kx, ky. This interpolation is the so-called stalled interpolation. And if you have this, then after this interpolation, it's just an inverse Fourier transform in all three dimensions, and your 3D image is done. The stalled interpolation is the only difference in the near field. That is the crucial step. The rest is exactly the same as for plane waves. Something one has to see is the effect of a spectrum on the image quality. If we think of imaging, it's always near field. I just want to motivate why. Here, what I show here is the spectrum, so or in other words, the signal each antenna sees at 2 meter distance from a 60 centimeter wide bar, just in 2 dimensions. So the first antenna sees almost no signal, the second antenna sees a higher signal, and so on. So if we reconstruct from these antenna signals here the entire image, you see the bar completely reconstructed. So the distance is reconstructed by the delay, and the angle is reconstructed from our spatial Fourier transform. So you can completely reconstruct the object. If we restrict ourselves, so we don't have an 80 centimeter wide antenna array, but a 40 centimeter antenna array, so it's just smaller, you only see a part of the information. The rest is just scattered away from your imager and lost in free space. If we do that, we lose signal, and so we cannot fully reconstruct the image. What you see is the center, because what is scattered from the center is still measured from the radar array. And you see the ends of the object, because discontinuities tend to scatter in all directions. But you don't see it completely. And if you play this game even more, you just say, okay, I want an integrated radar, so let's make it smaller. You get more and more away from imaging, because you just lose too much from the spectrum. And you don't also see the discontinuities. So you get away from imaging to localization. You know that there is a reflector, you know the direction of a reflector, but you don't know how it looks like. You can do that, but that's detection. The obvious question is when, okay, in a camera, and if I take my mobile phone out, I have such a small lens, and I can see people on 10 meter distance, not a problem. How does that work? Practically, it works because people have a rough surface. If you take visible light, we are talking about nanometers wavelength, hundreds of nanometers wavelength. For that, your entire body is a rough surface. And this is scattering in all directions. So you don't have a smooth bar, you have a rough object with an arbitrary phase error that is scattering in all directions. And when you reconstruct the object, if I do the same with the radar, so I say my 60 centimeter bar for the 20 centimeter small radar is arbitrarily rough. Every point here scatters in all directions, and when I see it as a rough object, but I see it. But a perfectly smooth object I would not see, because it's scattering anywhere. Like making a video of a mirror, you see the background, but you don't see the mirror itself. And if you look at the results we get from smaller and from larger modules, you see that. We are developing very small integrated radar modules. Here, for example, some of you might have heard of a Smokebird project where we developed MIMO radars at 120 gigahertz with 24 receivers and 24 transmitters, all integrated at 25 centimeters. It would be obvious to say, okay, if my wavelength is so small, because the frequency is so high, we should be able to see images. But effectively, smooth surfaces are hard to see, you just detect. If I stand in front of this radar, you see basically some rough reflections, depending on your body mass index at different points. And you see the point spread function, some spread which is given by the antenna distribution. The story is completely different. If I go to a complete imager, like we see here, so where you get the entire spectrum, and you have a person standing in front of it, you get the entire spectrum, then you can actually reconstruct the shape, and depending on the frequency, you can look into people's face. So that is the fundamental difference between detection and imaging. If you want to detect, you can integrate. If you want to image, you have to see the near field, so your imager needs to be more or less wider as the distance of the object to the radar in order to get in the entire scattering spectrum in the image. And with this small impression, I would like to close my talk for today. Thanks for your patience with all these formulas and theoretical explanations. And I'm looking forward now to a nice discussion just on the board behind me. Thank you.
Yeah, thank you, Reinhold, for this insight into science. It was quite challenging for me as a layman, but I hope that you as a radar interested people and maybe radar experts understand everything. Well, if not, now you have the chance to ask questions. Well, we are very sorry. Unfortunately, we made a small mistake when setting up this live event. So you will not be able to use a chat or something like that. So we cannot change this shortly. Please send us an email to pr@fraunhofer.de. You see it here below. The email address here is it. And then informally, only the question, and then we will answer it today. Yeah, I hope next time it works normally. So one of you used this way instinctively and asked the question, one moment. Oh yeah, this is a German question. Wie und woher kommt die Tiefeninformation? Maybe you can translate it.
Sure. Thanks for this question. The fundamental function of a radar is a distance detection. So if you would have a single antenna which is transmitting a signal to an object, so something here, which is reflecting back, we have a certain time delay, which is tau, so practically 2 tau, because it has to go there and back. So if we want to get this information and we measure in the frequency domain as I explained, you would have a phase shift in the signal, or a signal which is coming back, measured signal of t or of f is e to the power minus j 2 pi f times 2 tau. So we have a linear slope of a phase over frequency depending on the group delay. And that's exactly where we say, okay, I can apply a Fourier transform on that. So a Fourier transform, or an inverse Fourier transform on the signal is nothing else than the Dirac, t minus tau. And that basically means I get a spectrum with a peak direct of the delay. So in the delay, what is the delay? The delay is just 2 times the distance divided by the velocity. And that's why you get the distance. So, and if you now take lots of antennas, you get many distances. We compensate the phase for the direction. We have a distance, and so you have your distance information as well as your angular information. That's the fundamental concept of that.
Yeah, great. Here the next question. The highest possible cross-range resolution is lambda quarter. What is the physical background?
That's the so-called Abbe's law of diffraction. If you have a grating, then and you illuminate this grating, you will get a direct reflection, which is the first order reflection, and you get diffraction, which is the first order diffraction, second order diffraction, and so on. So if you want to see just the distance, the first order reflection would be enough, or third order reflection would be enough. You don't need diffraction effects. But if you actually want to see that this is a grating, yeah, you need to detect these signals. And if that tends to be lambda by 4, so if that distance here is lambda by 4, you get the direct reflection, and you get the diffraction directly at plus minus 90 degrees. So that is the limit. The infinite aperture would detect directly the first order diffraction at lambda by 4. And if you then say, okay, everything, all objects which I can detect can be expressed as a sum of these gratings. Yeah? when you say, okay, the smallest detail which I see can have a periodicity of lambda by 4, because the highest diffraction which I can see is plus minus 90 degrees. So if I cannot detect the diffraction caused by the shape, it's gone. It's out of my detection spectrum, and that's why I'm limited to that value.
Okay, thanks. Here, and a second question of the same person. I understand back projection as a kind of multilateration. Is that right?
Yeah, depends on what exact level you're thinking. Yeah, it is, but it's not triangulation. What you would do in a multilateration would be just to get the position. Yeah, you have an antenna here, and an antenna somewhere else. On 2D, it would even work with 2 antennas. You work out this distance, and this distance, and you get the position. But you get the position only. You don't get an image. If I have now an object which is arbitrarily distributed, and I want to get an image of that, then I'm basically trying out different positions, compensate the phase, and focus on different points. I focus on this point, this point, this point, this point. That forms me basically the image. So a triangle or a multilateration for me is just giving me the position of some object, while back projection is giving me the shape. And the image quality of the combined signal or of the image is then improved by getting more antennas. If you do a multilateration, you just want to know the position. If you have 3 antennas and if these 3 antennas are working perfectly, you're done. It doesn't get better with the 4th one or the 5th one. If you want to get a reconstruction of an arbitrary object, of course, every antenna helps.
Okay. Next question. How can we decide on an optimal aperture length in practice, especially when we are not sure the sizes of the objects could be measured?
Okay. Yeah, what's the optimal aperture size? Of course, it's always the best solution under the given circumstances. Yeah. So if I think it from an imaging point of view, I would say the more, the better. But this is just the first view on this problem. What you would try is to get the maximum diffraction spectrum out of the image. If you would know your object and you know what the scattering spectrum is, you could adapt directly to this object. I've never seen a problem so far where I know it to such an extent, so that is probably out of the equation. But what you know is that your antenna is just seeing a certain angular range. So let's say my antennas would focus like this, and my object would be here. Then this antenna is absolutely useless because it just doesn't see this object. So from an imaging point of view, I would say all the antennas which are not seeing the object due to antenna opening angles are useless when you make it smaller. Everything else depends on your problem. What is the resolution you want to see? Yeah? Usually I would, as an engineering approach, I would say I'm living with lambda by 2 and I adapt my antenna opening angle, so I limit my aperture size. But that really depends how much you want to invest and what image decodation you want to accept at the end. Yeah.
Thanks for your answer. What was the role of scold interpolation?
Scold interpolation basically removes the difference between near and far field. So in the so if you say, okay, I'm looking for z as a function of k0. I have a certain sampling in x and y. Let's say, okay, I have a certain sampling in the x domain. So if k squared is kx squared plus kz squared, if k is as high as kx, and kx is defined by the antenna spacing, then kz is 0. And in the far field, if I have a very high number, kz is almost exactly k0 because kx doesn't matter anymore. And in between, you have, in the near field, you have a nonlinear slope. So you kind of try to interpolate here. In the far field, this interpolation is useless. But here, you try to get a linear spacing for kz. And this interpolation is a salt interpolation. So it's more and more critical you're closer to get to the object. And kz over the frequency is basically then less and less nonlinear. So that basically compensates for nonlinearity errors you have in close and near field. That's the role of salt interpolation.
Okay, thanks for your detailed answers. Yeah, here's the last question. Have you experimented with imaging using compressive sensing and a small antenna?
It depends what you mean with small antennas. Let's interpret it in a way, a small antenna array, I guess that's the meaning. So yes, we did some experiments on that. It's not for imaging, it's not the typical way you would do, because for compressive sensing you need preliminary information. And the usual case you assume there is that you have a sparse scene. So you're not reconstructing the image of a person, you're reconstructing 3 point scatters in space, or 5 or 6. We use it from time to time, not for person imaging. The problem is, if you take a small antenna, you say, okay, I have my 3 point scatterers here, and they are scattering in all directions. And I have a small antenna array. I would have to take this preliminary knowledge that I look at this in order to extrapolate, and that usually doesn't work really. What works well in compressive sensing is to interpolate. So you don't measure a dense antenna array here, but you measure some part here, some part here, some part here. So you have a random distribution of antenna positions, which is wide, but it has gaps. And you can interpolate these gaps by taking the preliminary knowledge that my image cannot look arbitrary, but has 3 scatterers, 4 scatterers, something like this. And that works pretty well. Just measuring with a small group array and then kind of inventing resolution doesn't work, because you don't have this information.
Yeah, thank you again. So those were all the questions for today. Thank you again for your participation. I hope you enjoyed it. Tomorrow morning you will get another short survey as usual. We would appreciate it if you would take the 2 minutes and answer the 4 questions. On Friday you will also receive the presentation slides from today. And if you want to share the presentation with colleagues or friends, 3 weeks from today it will be published on our YouTube channel Fraunhofer FHR. Finally, let's take a look at the next lectures. The next talk is on March the 1st, 2022 on clutter-free localization by harmonic radar at 60 and 120 GHz. So if you haven't registered yet, do it now. See you in 2 weeks. See you then. Bye bye.